Let's say I have a reaction where I have H2 reacting with I2, and that gives me HI. Now, at this point in time, I want to be cognizant about the arrow. So I'm going to depict it with this kind of an arrow, showing that the reaction is going back and forth. Okay. I'm going to balance the reaction. So I have H2 plus I2 gives 2HI. And now I want to try to measure what happened. So I want to get some quantitative measurement. So to get the quantitative measurement, I'll introduce a term called K, capital K. Pay close attention. In the last chapter, we also looked at K, right? The rate constant. That was a lowercase K. Okay. So for reference, rate constant is this K. This, the capital K, is equilibrium constant. Now, if you go onto the internet and you look for capital K, sometimes you'll see K, sometimes you'll see K with a lower case C. That C stands for concentration and molarity. Okay. So if I had all these terms out here, then the way Kc, or the equilibrium constant, is defined is you put the products raised to their coefficient over the reactants raised to their respective coefficient. And that gives you a number. If you know the concentration, if you know the molar concentration of this, this, and this, you can plug them in, you'll get the value of Kc. If I give you this reaction, can you write the value of Kc for this reaction? That's exactly what it'll be. Now, here's the cool thing about this. In the last chapter, you could not write the rate law by using the coefficients, right? Remember that? So this is a point of confusion. Remember, when you're trying to write the rate law for a reaction and a reaction is given to you, don't use the coefficients. The only time you could do that is when you had an elementary reaction. But in this chapter, we're talking about equilibrium constants. For an equilibrium constant, you will literally take the coefficients and raise them to the coefficients. Okay? All right, let's try another one. Try this one. All right, so who wants to help me out with this one? Okay, hydrogen raised to what? Okay, times. Okay, raised to 1, because there's 1 in front of C. Okay, over, which is CH3OH. That's it. If K is much, much greater than 1. Now in the lab, I used 1,000 because you need to cut it off somewhere. Much, much greater than 1. If I say 5, is that much, much greater than 1? Some people would say, you would say no. Some people would say, well, it's 5 times 1, so it's much, much greater than 1, right? So it kind of leaves a little room for interpretation. So in your book, if you look at your book says much, much greater than 1. But basically, if it's over 10 to the 3, okay, then what that means is you have essentially products with barely any reactants. But if K is less than 10 to the negative 3, you have essentially reactants with barely any products. And when K is in between 10 to the 3 and 10 to the negative 3, then you have a good amount of both. Okay. So let's take a look at some examples and try to understand this. Okay. Take a look at this reaction. H2 plus BR2 to HBr. Turns out the expression for K. Now let's get some practice. Don't just write down what I'm saying. Go ahead and write the equilibrium constant for this first, the expression. That way we'll get some practice, so we won't have to think about it too much. Okay, equilibrium constant should be what? K is equal to HBr raised to the power of 2 over H2 times Br2. That's my equilibrium constant. The value of this is actually, experimentally, it was determined to be 1.9 times 10 to the 19. Here's the thing about equilibrium constants. Equilibrium constants are unitless. So don't get too caught up about the units of an equilibrium constant. This is one place where you'll have a little bit of a reprieve from trying to figure out the units of something. Equilibrium constants do not have units. 1.9 times 10 to the 19. Now take a look at what we just discussed out here and tell me, where does this lie? Do you have yes. Experimentally determined. We didn't do any math to derive it. We basically did it in a lab. I'm just giving you the results. And all we need to know is we just need to take a look at those results and compare it to what we have up there and try to figure out, well, in this case, are we going to have predominantly products, predominantly reactants, or a good amount of both? Predominantly products. Is that what you were going to say? All right, predominantly products, right? Because see, look at that number. That is huge, right? That's just not little over 10 to the 3. That is like way greater. That's what, when you read your book, you'll see in your book, it says much greater than 1. What is much? Is 500 much greater than 1? I would say yes, right? We would all say yes. Turns out it's not sufficient. It's still not big enough. What is big enough? That's big enough. Make sense? Okay, let's take a look at another one. Where here's another reaction. N2 plus O2 gives us 2NO2. And K for this, go ahead and write the equilibrium expression for this while I write the value of K, 10 to the negative 31. All right, so this should be what? NO2 raised to 2 over N2 times O2. So, what do you think about this number? What does this tell you? More reactant? Look at that reaction very carefully. That's correct, by the way. You have a significant amount of reactants. But look at that reaction carefully and tell me, what implication does this have in our lives? If you look at that reaction, this reaction that I gave you, this one, and here's the equilibrium constant that I gave you, tell me what implication does that have in your personal life? If that reaction had a high equilibrium constant, guess what? We wouldn't be alive. No one would be alive, because all the oxygen would react with the nitrogen in the atmosphere, and we'd have nitrogen dioxide. Guess how human beings do by breathing nitrogen dioxide? Not well. Let's putting it lightly, not well. We cannot survive on nitrogen dioxide. See, now, so tell me, coming back to your initial question, does that mean there's anything happening out here? Is there any of this? Oh, sorry. Is there any of this in the atmosphere? Because basically what this equilibrium constant is telling us is that we have a chunk of this, right? Does that mean that there's nothing here? There's much less of it, but significantly less. So less we can barely detect it, right? Now, when we talk about environmental pollution, for example, when you're burning fossil fuels, things like that, when you're driving your car, this is actually a byproduct. Okay, so the more equipment you use that burns all these fuels, you're going to have more and more of that in the atmosphere. Right now, carbon dioxide is our big concern, okay? Because that's contributing to global warming. This is less of a concern, but this guy is hanging out there. Once we're done with solving the carbon dioxide crisis, if we do, then we can turn our attention to this guy, okay? But luckily for us, we probably don't have to do much because chemistry is in our favor because of that number. Does that make sense? So even if that guy gets produced, the equilibrium is going to say, hey, you know what? We prefer pure nitrogen and pure oxygen. Now, there's another implication, not just the oxygen implication. What's the implication of this guy hanging out there? How are we going to eat our food? What do plants need? Nitrogen. Guess what happens when lightning strikes? It breaks down atmospheric nitrogen into atomic nitrogen. And that atomic nitrogen gets into our plants and gives the nitrogen that the plants need. And guess what? If our plants don't get nitrogen, what do we not get? Huh? That's right. But more importantly, well, again, food is important. But if you want to get really technical about nutrition, no. What is in? Go ahead. Not carbon. Protein. I mean, everybody's obsessing about protein, right? I mean, everywhere you go, people are saying, hey, you know what? We're not getting enough protein to eat. Yo, let's grab a breakfast sandwich with 19 grams of protein. Hey, I'm even going to sell you water with 15 grams of protein in it. So everybody is trying to get excess protein, right? Do you know what protein needs? Every protein molecule needs nitrogen to form. Without nitrogen, there's no protein. Of course, you got to grow the plant and get the protein. Now, guess what? You're like, well, I don't care about plants. I'll just get my protein from beef. You won't have any beef if there's no plants, right? Because the cow's got to eat plants, right? So really, your source of protein is actually the nitrogen in the air, believe it or not. Go ahead.